And as the term goes on, I think more and more people are switching to doing this asynchronously. The numbers actually go up during a lecture, which just kind of makes it weird. It's like people kind of dribbling in late into a lecture. Um, yeah, dash bonds are going back into the plane always. Wedges are coming out of the plane. Yeah.
Okay, now you just said it confusing. You said dashed bonds is out of the page and wedged is out of the plane.
No, dash bonds is back into the page. So dash bonds is away, back into the page. Wedged, like the solid wedges, are out of the page towards me. You're kind of like poking you in the eye. So dashed is going away, wedged is coming towards, or solid is coming towards. Does that help?
Okay, it's just just trying to help with just trying to clarify myself with 2S and 3S and so on.
Yeah, exactly. Dashed means going away from your view. So over here we have a dashed to the epoxide. That means the epoxide is behind the plane of my screen. Whereas we have a wedge to this methyl group. That means that methyl group is coming towards me, out of the screen, towards my face.
Okay.
That's what that means.
But the straight line I see sometimes into the plane of the page.
Straight line is in the plane of the page. So a straight line is flat.
Mm-hmm.
There's no three dimensionality indicated in a straight line.
Okay, thanks. So just to clarify, the wedge one, that's out of the page towards the viewer, and the dashed ones, that's back into the page away from us.
Correct. Yeah, and that's universal. That's always how this is shown everywhere. So if you've never seen that before, I know it's confusing. And one of the great challenges I think doing this, teaching this, is I can't unsee it now. Like I can't put myself back into the perspective of not interpreting it that way. Like my brain just automatically does that. And it's a huge it's always a trouble teaching something. Like if you guys are teaching anything to anybody, sometimes it's really hard to get back into the mindset of the person who's seeing this for the first time. So yeah, correct. This dashed line indicates that this is going into the page away from me. This wedged or solid line indicates that it's, sorry, you can't see my mouse because I'm using the wrong thing. This dashed line here indicates that we're going into the page away from me, whereas the wedged line next to it is out of the page towards my face. Okay. So last class we wrapped up here where we were talking about, we divide into like the greens and the blues, like some sort of 6th century Byzantine chariot racing team fan group. They divided into the greens and the blues, and there was like the reds and the whites as well, but they were minor teams. So almost went into Byzantine history instead of doing this thing. And what we went with was that in this case, the green was the major product because it was the more accessible carbon to get to. And the reason that matters is because there is no net charge on that epoxide. Okay. But, there's always a but. So if we take, I don't know, you know what? I'm sick of cyclohexanes. We use a cyclopropene. This is a stupid molecule. I actually think that this would probably just explode instead of doing the chemistry I wanted to do, but we'll pretend. So we're going to make an epoxide out of this, except we'll make an epoxide a different way. What we're going to make it by is we're going to add BROH and then number 2 is sodium hydroxide. And this is going to end up with an epoxide for us. Just like I'm always biased, I'm drawing it out of the page. It's completely arbitrary. I could have drawn it into the page. That would have been fine. It's just I like drawing dark wedges. I don't like drawing dashes if I can avoid it. So this is what's going to happen. So a very typical question on a final exam would be, provide me the mechanism for this transformation. Give the mechanism by which this happens, kind of thing. So thinking about that and going, okay, first thing, and the 1, 2 means you do 1 first, then you do 2. So 1 first, BROH. Okay, we've seen this before. You know what? I'm going to add a methyl group just so that we have something to keep track and differentiate the two sides. Okay, so the first thing I need to do is I need to think about, okay, double bond, BROH, that's kind of that, it's kind of like that BR or iodine. It's in that ballpark of things that's going to probably make a 3-membered ring. So if I'm thinking about how that reacts, I look at my periodic table and I think how that bromine OH bond is polarized, and it's polarized that way. I'm arbitrarily attacking from shit to make this work. I have to arbitrarily attack from to give me the exact product I want. I have to arbitrarily attack from the bottom. It's arbitrary though. Perfectly correct to do it from the top. Okay, I just looked over the chat and there's like suddenly an explosion of questions. I just want to know when atoms like I just want to know when atoms like oxygen and that is an incomplete sentence. Um, well, if it's making 2 bonds, it will make 2 bonds. So that was an epoxide. That means oxygen's making 2 bonds. That's what an epoxide is, and it did that because it was the only thing that was present to do that. Major and minor. Um, Major is the things you expect to use to get doing the examples, like doing the chemistry, drawing the mechanisms. Yeah, Andrew. Okay, so I'm gonna. Man, this is like the most active the chat window's been in weeks. This is kind of awesome. So, on Mobius assignment, for example, I say major product. You know what? You stick 2 molecules together. There's 10 to the 23 molecules in there. Everything freaking happens that can possibly happen. Major is the stuff that mostly happens. So mechanistically, it makes sense. You can draw a mechanism using the kinds of things we've done, and it works. You can get all sorts of other things because there are all sorts of little side mechanisms happening. Because, okay, there's a difference in opinion in organic chemistry. I draw them all like this. This is because this is the way we draw them, the way we've always drawn them, and it makes sense of the chemistry. But I think there's increasing understanding that every single reaction does not involve 2 electrons moving at the same time. Everything is single electrons transferring over and then making new bonds. So suddenly a million things become possible because then you start thinking about electrons being just clouds of probability of negative charge. And suddenly you can start sticking things to anything and breaking bonds all over the place. And that happens. When you have 10 to the 23 molecules, anything can happen. So minor products, very minor products, basically anything in a known universe can be formed. Major products are the things you're actually mostly like 50% plus of the things are becoming that. Minor products, a few percent. In all the questions, I'm asking for the major ones, and that's the ones you get from drawing the mechanisms according to the rules of the mechanisms that we draw. How will we know when to draw a specific bond for an element, dashed or wedge? Mechanistically, sometimes one implies the other. So we've seen that with the previous thing. So when we opened the bromoniums, those three membered rings with the bromine in it, with the nucleophile came in opposite the bromine. Didn't matter if the bromine was dashed or wedged. The other one would be not dashed or wedged. It would be the other one, because that's just the way that goes. So that's when it matters. Otherwise, like in here, it's a flat molecule. You're going to get both. You could write and enantiomer if you wanted. Or you could draw the enantiomer. I just don't want you to have to do that. So, you're going to get the same amount of this. Exactly the same amount. Because it's a flat molecule, starting material, there's no chirality, everything's equal. Why isn't the plus on a tertiary carbon? Because I messed up, and it should have been, but this is what the major compound is. This is kind of like a resonance structure. So I am going to correct that because you're right, Andrew. And that should be the major one. Somebody asked me, why do the amounts of the two reagents matter? They often matter a lot because ratios of different reagents can give you clues on what's going to happen. So if you have one reagent where you have one of it and the other one where you have a million of it, and they're competing for a reaction, the one with a million molecules floating around is going to be the one that reacts. So if you have a 1 to a million shot of something, you don't bet on one, you bet on the 999,999, because you're going to be right 900,999, whatever, big number, lots of nines. Okay, so first step, we do things we've seen. That's cool. Now we have OH minus. That's going to come in at the more positive carbon. And it's going to push the methyl group that was there down. We're going to come back to this kind of stuff, why all this happens in a bit when we talk about the SN2 reaction. Okay. Now we've made these. This has been the end product for some of the things that we've seen in previous lectures. Now, if I take this and I treat it with number 2, so lots of sodium hydroxide. So sodium hydroxide is a base. And the fastest reactions are acid-base reactions. So you're looking around thinking, is there anything acidic on this molecule? And hopefully you're looking and you're thinking, well, that hydrogen there is kind of acidic. It's not super acidic, it's an alcohol, but my base is an alcohol. This is kind of a wash. It's a little bit the same on both sides. Okay. Now, this is going to be the next thing that happens is a reaction we haven't gotten to yet. We're going to spend quite a bit of time on it. It's called the SN2 reaction. I really hate naming reactions, but sometimes it works. And what we're going to do there is we are going to use the lone pair on the oxygen to kick this out. And that gets us our product. Plus Br minus is the leaving group. It's a different way to make an epoxide from using MCPBA, which is what we saw last class. It also results in an epoxide. Okay. So I can make epoxides this way. Now, if I take that molecule, this is the name of a reaction. It's not a reagent. It's not sulfur. It's not sulfur dinitrogen. It means substitution, nucleophilic, biomolecular. But we'll get back to why that matters. What I just want to say here is that this is a different way to make an epoxide. Right now, this isn't. I'm not going to test you on this until we see a discussion of the SN2. We're going to come back to this concept. But if I have that epoxide, and let's say I treat that with, we can actually just go backwards almost. Now, just remember where we came from. We came from this guy here. OH is on the more substituted carbon, Br is on the less substituted carbon. Now, if I treat this with HBr, as I said, fastest things known to man in terms of reactions are acid-base reactions. H plus is an acid. Are there any reasonable bases around? We've been kind of using double bonds as bases. If we had double bond here, we'll react with the H plus. That's kind of double bond acting as a base. Well, here I've got the oxygen. It's got a lone pair. It's a Lewis base. Now I protonated that oxygen, and that gives us a Br minus. Okay, now if that oxygen was neutral, the Br minus would look for the easiest to access carbon. But the oxygen is not neutral. It's positive. And so this reacts identical if we had a chloronium there, which we've seen. No difference. The difference is chlorine, of course, can't decide to be neutral in that case. Oxygen can, because it can make those two bonds. Chlorine can only make one. And in this case, what we're looking at is which of these carbons has the bigger positive charge. And hyperconjugation tells us, yeah. And hyperconjugation tells us that this is the bigger positive charge on that carbon. And so the bromine is going to come in and attack that carbon. And again, we're going to flip the methyl group up, so we're going to come in from the opposite side, and we get our product. I'm just, why is there a Cl? It's just identical to. It reacts the same way as. So if you're the epoxide, we've seen how these chloroniums react. It's still an epoxide. It's a protonated epoxide, though. So what we've done here, if we summarize all this, nucleophile, basic conditions, goes to least hindered carbon. Whereas nucleophile acidic conditions goes to carbon that makes a more stable carbocation. Yeah. What it means is yeah, exactly. So just this. So we can influence which carbon is attacked by whether we add acid or not. And that's why this happens. So it gives you a different result under acid and base. And the reason why is something we're going to keep coming back to. The acid thing you've seen. This is nothing new. This is exactly how everything else reacted that had a positive charge on it, like chlorine or iodine. The base one is different, but it makes sense when you think about it. If there's no positive charge building up, then there's no reason for it to attack one or the other like you have here. And molecules are lazy, and they're going to find the easier target. Hindered is the word. So, what happens to the sodium? Oh, who cares? Nobody cares about the sodium. It wanders off and does something. Don't care. Only care about what happens. We generally just care what happens to the carbon chains. Carbocation. I will try and write neater. Zoe's favorite type of anion because it's a cation. Okay. So that was epoxides. So what we want is okay. So if we make an epoxide, and if I treat this with H plus in water, that's acid. You know, I'm gonna use the power of color. It's water, so it's blue. I'm gonna pretend that was at all planned. It wasn't. It's just the first color I hit that wasn't red. We get that. Whereas if I treat it with sodium hydroxide in water, okay, we're going to get that product. Same product. Well, I guess they're enantiomers of each other, but you get both enantiomers anyways because the strand material is flat. But the OH is at different places. These are both cis trans diols. The hydroxyl groups are on opposite sides of the ring from each other. Well, what if I want a cis-diol? So what we're going to use is we're going to use a reagent KMnO4. Sodium hydroxide, water. So not a bad idea once we go through all these to start drawing up lists for yourselves of the mechanisms, practice trying them out, put them on flashcards, put them on pieces of paper, do whatever you do that works for you, just to categorize and organize these. So what is this thing? Well, this is why I hate metals, because no one should make that many bonds. So that's KMnO4. There's a K plus floating around somewhere. And now we're going to do something for the first time this course, which is we're going to use the double bond as an electrophile. It's been a nucleophile every time. The electrons have started from the double bond. Now they're not going to. Now I'm going to use the electrons as oxygen to attack. You know what? I'm going to flip where that methyl group is. And we're going to draw something that doesn't exist. Just so that we're convenient on this. Note that I'm putting the negative charge on the less substituted carbon because of hyperconjugation. It's the opposite effect we expect for the positive charge. If we had a positive charge, it would go on the other carbon. So a negative charge is going to go on this carbon because it just wants to be different. And like most other Instagram influencers, it ends up being completely predictable. So we have the negative charge over on that carbon that's looking for something to do. We're going to attack the oxygen, which is just a little weird. And that's going to push electrons onto manganese. Those of you who are taking inorganic chemistry, electrons moving onto metals isn't all that weird. Those of you not taking inorganic chemistry, good for you. So if we're looking at this is manganese 7. The manganese is at oxidation state 7. It's making 7 bonds to oxygen. We're going to bring it down from that to manganese 6, really. But we're not done. Keep track of our negative charge, still there, but now it's on the manganese. That just looks awful. There's just something wrong with that. And deleting it would be nice, but that's not what happens. So what we're going to do is I'm just going to break the bond onto that. It's going to get rid of that ugly negative charge on manganese and put it onto oxygen, which makes me breathe a sigh of relief. I'm just going to put in some stereochemistry here. So note that the oxygens are being delivered from the same manganese, and there's no way for them to be on opposite sides of this ring. They have to be on the same side of the ring. My palm is activating this. There we go. I want to point an H there, but I don't have that yet. And now I'm just going to draw the manganese floating over here just because there's an arrow in the way, and it's going to be neater. So if we're keeping track at home, and we're all at home, that's now down to manganese 5. It went from 7 to 5. And we've stuck 2 oxygens onto our carbon. But we still have this irritating oxygen manganese bond that we do not want. So how do we get rid of that? Well, that's where the sodium hydroxide comes in and saves us. So I lost the oh, I did. Yeah, I dropped the methyl group. Thank you. So we're returning manganese back up. Manganese can accept lots of electrons. It's got d orbitals. That's a 5, is what that says. Roman numeral 5. I don't think that's any neater. Just keeping track of how many plus charges are kind of on the manganese. We're back to this negatively charged manganese, which is ugly. We can solve that the same way we solved it a few seconds ago, which is break a bond to oxygen. Now I have negative charges. The chance I've got 2 negative charges on the same molecule is pretty low, so probably I would have taken care of one earlier than this. But we've got lots of water around because we're like sodium hydroxide water. This is why I don't like doing this in PowerPoint, because I squish out of space. I guess I could get rid of the U Windsor branding at the bottom and just write over it. And then do it for the other OH2. There we go. Show this institution the respect it deserves by writing over its logo. Okay, so then we've got the 2 OHs there. They're on the cis sides, and everything's neutral. So we know we're done because everything's neutral. And here we've got a cis diol. Okay. Now, this works if this whole thing is done cold. This works less well if this whole thing is done hot. Why? exact same thing. Oh no, they get longer, Nulia. We're in for a real treat. Next class. I'm looking at the time. I'm going, it's 2:07. Next class. I'm trying to get these. They're really. These are what I kind of call miscellaneous reactions. They're things I want to cover. They're important building blocks for other courses. Um, they take a little bit of time to get into your head. So I want to get them done a little bit earlier. So I'm actually, we started with I think, practicing the arrow drawing. Hopefully you were practicing with it. We're now going to some of the most complicated mechanisms we see in the class. Then we reduce the complexity of the mechanisms, but we're going to increase the complexity of balancing different factors. Here we're not trying to balance any factors. It's this reagent, this thing gives you this product. That's how it works. Here's the mechanism. Blah. Um, we're going to be getting into the point where the mechanisms get pretty simple, but then you got to consider a million different things, and it gets tricky. There was a KMNO4 in the previous one. It just never did anything. It was just there because it was boring. Plug in before my phone, the thingy dies. Yeah, that was my computer. That was freaking out. Luckily, I've got my charger here because I was thinking ahead. It's supposed to be the chemistry that gives you the heart attack, Zach, not the blue screen of death. This is a Microsoft tablet. It doesn't really want to do anything ever. Like turning on seems to be a challenge. The keyboard occasionally works, but most of the time it doesn't. And so I spent a lot of time basically Googling how to make the keyboard work on one of these goddamn pieces of equipment. And figured it out, but it means I need to turn it back off and back on. So, anyways, sidebar. Really boring sidebar. My wife and I call those squirrel stories because she once called me up with a story about a squirrel, and it didn't go anywhere. There was nothing. The story was there was a squirrel. That is not an interesting story. So we call them squirrel stories because they're really boring stories that kind of go on a long time but don't actually ever go anywhere. And that is a really shitty way to draw it right at the top of the thing and I'm running out of space. So I'm going to draw it a little bit lower. And I notice as I'm getting older, I'm telling more and more squirrel stories. And I think it's worse in this context because you're a captive audience and I can't see your eyes glaze over. Okay, so we're going to get back to the same. Just there's a freaking manganese in there. Same place we were last time. Few steps in. But if we're hot, some weird stuff starts happening. Oh, there's a negative charge on the manganese. And that weird stuff is weird. So we're going to break this bond just like we did last time, except instead of the electrons going onto the oxygen like we did last time, they're going to go all the way down to the oxygen carbon double bond, single bond to make a double bond. But if oxygen carbon's making a double bond, that means carbon's going to be making 5 bonds, and carbon can't do that, so the bond has to break. And all I've got is carbon-carbon bonds. And those are hard. Just bear with me for a second. Yeah, the last experiment was cold. Nulia, that was so. I think Nulia referring to one of the Mobius questions. The Mobius questions asked you which one of these has that configuration. That's RS configuration. So you have to identify carbon 2, carbon 3, carbon 4, and is carbon 2s, is carbon 3s, is carbon 4s. It's just stereochemistry. We covered that. You can look back over it. You can look at in a textbook and read more. If my lectures didn't work, which they're not going to work for everybody, God, I know that. But if you're confused about R and S still, then look back over the textbook, look back over the internet. But I'm not going to cover it again today in class. So when keeping track of where the charge is, it's now moved on to this carbon. We've and there's still a methyl group here. Well, that's awful. I've got a negative charge on a carbon. But I can make a new carbon-oxygen double bond, kick the electrons onto manganese. Now, I'm fortunate that Dr. Drover is not here right now because I'm sure he'd have something to say about what I was going to do to pour manganese over here. I'm going to note with some interest, not very much interest, that what I've got, oh, come on, I don't want that, I want the pen. Stop panning. That what I've actually got is manganese 3. But I don't really care about manganese. It does look like a bat. What I care about is this thing here. So what we did, yeah, we just broke a carbon-carbon bond. That seems hard, which is why you need heat. So, to sum all this up, if I do this hot, I basically snap that double bond in half like a twig, and I stick in 2 carbonyls. If I do it cold, I get a cis diol. If I took, I'm just going to call that A. If I took A and I treated that with MCPBA, followed by sodium hydroxide and water, I would get a trans diol. If I took A and I treated it with acid and water, I would get the Markovnikov addition of water. I said Markovnikov addition of water. And if I took A and I treated it with BH3, followed by hydrogen peroxide, sodium hydroxide, I would get the anti-Markovnikov addition of water. And the H and the OH in this case are cis. These cases, they have to be trans, but random. Like random if it's the other way. There's 4 products you can actually get there. 2 products, I can't count. I have trouble counting. Okay, so we have trans diols, we have cis diols, we have the mono all on one, we have the mono all on the other, and we can cleave the whole thing down to 2 aldehydes. So all the same material, all doing chemistry with just adding oxygen basically to this double bond, essentially water in 4 of the 5 cases. But we've figured out, you know, if we're adding OHs to this, there's 4 things. We can add one OH on the left or the right, or we can add 2 OHs, and those 2 OHs can be oriented trans to each other, assist to each other. And we now have the tools to do all 4 of those things. Plus, we can just snap it open and give ourselves 2 carbonyls. We're at 217. I think that's a good place to leave that for today. That was enough of a sprint through oxygen chemistry with double bonds. Next class, we're going to talk about ozonolysis. So, if you want to get a head start and you're done your Mobius assignment, which is due at midnight tonight, you're very welcome to look up ozonolysis. This is weird. Yeah, of course I can go back. Yeah, any acid, H plus water, HCl, a little bit of HCl, a little bit of sulfuric acid, just whatever. Yeah. Okay. I'm tired. It's Friday afternoon. Like it's a little bit cold for patio beers, but I'm an Ottawan and we were built for this. Trans but random. Yeah. So this is Markovnikov, meaning it went through the more stable carbocation. This is anti-Markovnikov, meaning it's not Markovnikov. MCPBA was the reagent that we showed for making epoxides. It's this guy. Saw that last class. Yes, the textbook has quite a few questions. I've also put up assignments with far more questions and far more practices on these. All of these mechanisms are in the textbook. I don't think I'm covering. I'm not. I think I might cover them in a bit more detail. I sometimes find a textbook just says be like here, kind of brushing over the whole thing, not discussing the electron flow. But all of these, there's examples of all of these in the textbook. And in assignment 1 that I just posted, and actually you can do almost all of assignment 1 now. 2, assignment 2. You can do almost all of assignment 2 now, which is posted. And I'm going to try and post assignment 3 in the next few days, but that kind of gets into new chemistry that we haven't quite gotten to yet. Okay, I'm going to stop recording.